Hello, welcome to the introductory course for abstract algebra. Please like, share, comment, and subscribe my channel. Thank you. So in the previous video, we discussed about relation, and we define a function. We also saw the what the domain and range of relation, and we define also well-definedness, one-to-oneness, and onto-ness. So as you said, a relation is any subset of the Cartesian product of for x and y, whereby x and y are any sets, and the domain of a relation is any first components which is a member of x, says that the order pair x y is in R for some y in y. Also, we define a range as a set of all second components y, whereby this order pair is in R for some x in x. So this is a definition of domain and range, and we saw some examples. So a function is a relation whereby any first component is exactly mapped to the one second component. That is, you say if x is the first component, and if it maps to y and also it maps to z, then to be a function, then y must be equals to z. And we say a function is well defined, or we say any relation is a function. We can say that one also, but this is the criteria to check well definedness. That is, if x is equals to y, then the functional value must be equal. Then we say this is a well defined function. So for one-to-oneness, so this is the like an inverse of this condition here. So which is, if you have equal functional value, then first component is equals to 1. Then any function that satisfies this condition, we call it is a one-to-one function. So we can also use a geometry to check one-to-oneness, so which is a horizontal line test. So for example, let's have this function here. So let's say this is x to the power of 4. So as you see here, if you draw any horizontal line, and if the horizontal line touches the graph exactly 1 point, then we say the function is one-to-one, else we say it's not. So as you see this one here, the function, it touches the graph 2 times. That means this x to the power of 4 function is not one-to-one function. So but you can have another example. For example, if you have this one, if you can draw like this graph here. So it seems like x cube graph, x to the power of 5 or something graph. So as you see, if you draw any horizontal line here, the graph, the horizontal line crosses the graph exactly 1 point. So we say this is an onto function. So in general, for a polynomial f of x to the power of n, where n odd is an example of a one-to-one function. So for onto-ness, so the criteria is saying like this, so which is for every y in y. So remember, the function here is, I'm assuming that x is mapping to y. So for any y in here in y, there exists x in x such that f of x is equals to y. That means every element in y has a pre-image in x such that the condition here is satisfied. So then if the function satisfies this condition, we say it's an onto function. So we can also use the geometry to check whether the given function is onto or not. So here is we say horizontal line test, and for ontoness we use vertical line test. So that means if you draw a vertical line here, the graph must crosses the vertical line touches the graph exactly at one point. Then you say it's an onto function. So for example, if you see here circle, which is x square plus y square equals to, let's say, 25. So this is an equation of a circle, and as you see, if you draw vertical line here, the graph touches, the vertical line touches the graph exactly 2 points. So that means it's not an onto function. So this is, it's also not a one-to-one function. You can check by draw this one. So this is an example of both non-one-to-one and onto function. But but we can have an example for an onto function, like you can have this graph here. So if you draw here, as you see here, if you draw any vertical line here, so this is the line touches the graph exactly at one point. So it can be an example of an onto function. So this was the content in the previous video. So today we start by checking when do you say, like, two functions, if the functions are given f and g, when do you say they are equal. So we say a function f and g are said to be equal. First, they must have equal domain. So this is the first condition, and the second is they must have their functional value must be equal. Then if the function satisfies these two conditions, we say the two functions are equal. So for example, if you see f is given by this one and g is given by g of x equals to x squared and h is given by this, so as you see, the domain of f is, which is z, and the domain of g is also z, so they are equal. Now they pass the first criteria. Then the second is, what's its functional value. As you see from the definition, x squared is equals to this one, so which means they are equal. So these are examples. If f is equals to g, we say this one. But how about h? So as you see here, the domain of f is z and the domain of h is positive integers, a set of all positive integers, and these are not equal, so it doesn't pass the first criteria. So we say f is not equals to h. So what about the range? The range doesn't have, the range is what? So which is, as you see, f maps any member of z to its square, and the square of a number is always positive, so which means z plus, and the range is also z plus. As you see here, their functional value is equal, so it satisfies the second condition, but the first condition is not equal, so we say they are not equal. So the next is, how can you get a new function from the existing one? So to get a new function from the existing one, we use these operations here: addition, subtraction, multiplication, and division. So if you have two functions f and g, then we define an addition or subtraction of two functions, or multiplication or division like this, provided that the domain of f intersection to domain of g is non-empty. If it's empty, then we'll have an empty function, so it's not a new function. So, but here, for both of them, we use the domain of f plus or minus g. F times g is the domain of the functions are this one, domain of f intersection domain of g. But for this one, the domain is domain of F intersection domain of G without 0. So it excludes 0 for this one only, but the rest is the same. So we can get the new function like this. So another important operation is composition. So the composition says if you have this F and G, now to define the composition of G composite F, we need to check this one. So F starts F from A to B, then G must be starts by B and it goes to C to define this one. So G composite F is another function, it maps A into C, and the definition is here. So the domain is, before the domain, so similarly to define F composite G, we need to have, like, if G is B starts C, then F must start from what? From starts to C, and from starts from C and goes to N, anywhere, let's say Z. So the domain of F composite G is always contained in F, so it's clear. And the range of G composite F is contained in the range of F. So these are, like, if you are asked to find the domain of G composite F, you need to, so the set you will get is a subset of domain of F. Also the range for G composite F is a member of this one. So let's see, for example, if F is mapping X into this one, whereby the domain is here, and G is mapping X to 2 over X, then again the domain is here one. This is the domain of F, and this is the domain of G. So what is F plus G and F times G? So before you find F plus G and F times G, you need to find the domain. So what's the domain? So as you see here, the domain is minus 2 to this one, so which is minus 2 closed bracket minus 2 intersection all real number excluding 0. As you see, 0 is included here, but if there was not there, the intersection was this one, but since 0 is not included, we need to have an open bracket. That's why we split this one. So the domain is this one. We find the domain, then the rest is simple. F plus G of X is defined by this, so we just get this like this, and F times G is just a multiplication. So the important thing here is everything is simple, but you need to find the domain of F intersection domain of G, or the domain of F plus G and F times G. So let's see another example. F is given by this. Again here the domain is this one. That means, let's say, other way is set of positive real number. You can say so the domain is R plus, and the domain of G is, this is domain of F, and the domain of G is what? The domain of G is set of real number. So, and you are asked to find F composite G and G composite F. So here you see F maps R plus to set of, R into R plus, R plus into, then this is positive, again this similar, then G is from R into R. So f composed g and g composed f. So we will find like this. So what's f composed g? By definition, which is f of g of x, and our g of x is given by this one. So this is g of x, which is another way of writing is 2x plus 3. So we are substituting g of x in place of x, so which is 2 of x. Then f of x is given by square root of x. We are substituting x, which is our 2 of x plus 3. You get this one. And the g composed f of x is the similar, so which is g composed f of x. That is g of our f of x is what? Square root of x. So which would be g of this one. So in place of x we have a square root of x, that is 2 square root of x plus 3. So this is the way. So now what is the domain of f composed g and domain of g of composed f? So as you see, the f of g of x is the domain of this is the same as x in the domain of g, so that g of x is domain of f. You see? So that is f of f composed g is the same as f of g of x. See here? So the domain of this means the domain of this one. So we have x in the domain of g, this one. Say that g of x is, it must be included in the domain of f. So x is in domain of g. Say that 2 of x, our g of x is 2 of x plus 3. So the domain of f, which is, it says the set of real number, which has to be greater than 0. That's how we used this here. So now 2 of x plus 3 greater than or equals to 0, which implies 2 of x, which if you take this one to the right, then equal minus 3, then dividing both sides by 2, you get x greater than or equals to minus 3 over 2. So that means every real number which is greater than or equals to minus 3 over 2. So that's the domain of f composed g. Similarly, you can get the domain of g composed f. So which is x in the domain of f, says that f of x in the domain of g. So our f of x is given by square root of x, and remember the domain of R is set of real number. But here, as you see, square root of x is x must be always greater than or equals to 0 in order to be defined. So because the square root of negative number is not a real number, so we are just considering only the positive one. So that's why you get this one as a domain of G composed F. So this is your exercise for you to try. So if you have given F and G, and if they are 1 to 1, so can you say that F plus G is a 1 to 1 also? If it is 1 to 1, then you can say, you can show by giving the proof. Or if they are not 1 to 1 in general, please write you the example. Give some 1 example or 2 example just to disprove. So another important function is the inverse. The important concept is the inverse of a given function. So a function has an inverse if and only if it is 1-to-1 function. So if a function is 1-to-1, then we can get the inverse of that function, so which is written like this one, yx, just inverting or changing the position of x and y, because f is given by the order pair xy, says that x is in x and y is in y. So this is the function definition, and to say it's invertible, to find the inverse of this function, so just interchanging the position of x and y. That's how you get. But remember always, to be a function has an inverse, it needs to be a one-to-one function, else we can't get the inverse of a function. So another important thing is, if you know a function f, then like sometimes if the function is given and it would be hard to get the inverse, the domain in range of the function. So if the function is one-to-one, then you just easily find the inverse and get the domain in range. So then you can associate. So which is the domain of a function, the inverse of a function is the same as the range, and the domain of the given function is the same as the range of this one, the inverse of a function. So the cancellation law also tells us, if you have a function and if it is invertible, then this is always equal if the composition is equal to x. So it's similar to like an identity function, we'll see later. So let's see an example. So if f is given by x to x is in the set of natural number, then what is the inverse? So it just so to x says that x in n. So this is one way, but the other way is it's important to write the inverse of a function in the formal way. That is, now as you see here, f of x, which is for us it's y, which is equals to x. Now solve for x, so it will be x equals to y over 2. You get y over 2. So this is, now then the third step is f inverse of x equals to x. So substitute x in the place of y, then you get x over 2. So f inverse of x, so this f inverse of x can be written as the set of all x, x comma x over 2, say that x is in what's n, yeah. So this is the formal way of writing the inverse of a function, but this is also another example, another solution. They are the same. So how about this one? So you just interchange, so which is 4 1 6 2 and 4 3. So this is the inverse of f. So the next is an identity function. So this is special function. So we define an identity function is, so for an unempty set x is given by this one, so which is a mapping x into x defined by this one, now of x equals to 1, x for every x in x, and we call this is an identity function, which is a special function. And you see now this one, f inverse of f inverse composite f, we say before, which is x, and we know that this is also defining, mapping one of identity of x, I of x is equals to x, so they are equal. So we are considering f, which is x to y, and f inverse, since it has an inverse it must be y to x. So f composed, this one, f inverse composite x means, so it starts from this one, f inverse of x, so which is f inverse of f of x, so our x must be taken from x, that's why we say it is 1 over x, and f composite f inverse of f inverse of x, as you see the domain of this one is, it starts from y, that's why we say 1y. Now let's show that this function f, which is given by f of x, which is equals to 3x minus 2, where when x is from R is a 1-to-1, and if it's 1-to-1, then definitely have an inverse. So how do you say, how can you show that this is a 1-to-1 function? So remember that always you need to check well-definedness. So well-definedness is a must for a function. So to check well-definedness, let's suppose that the first coordinate components of the order pair is equals to 1. Or take two equal elements from the domain. Then as you see, if you multiply by constant 3, then the equality preserves. Again, if you add both sides or add 0, so it doesn't change. That means here you see it plus 2 minus 2. You see I am adding 0 here. That's how this comes. So this one, if you take this one plus 2 to the left, you get this minus 2, and this minus 2 kept here. So adding 0 to any number it doesn't change anything. So this is the definition of f of x, and this is the definition of f of y. So therefore we say f is well defined. So always remember, before doing anything, especially in this course, you need to check well definedness. So the next is to show one-to-oneness. So suppose that to check one-to-oneness, we said that you need to take two functional values. Then you need to check that whether these x and y are equal or not. So let's suppose f of x is equals to f of y. Then we have this one. So if you add both sides 2, so that means adding 0 again. So or taking this one to the right, then you'll get 3x equals to 3y, and dividing both sides by 3, you'll get x equals to y. So we show it's 1-to-1. So if it's 1-to-1, by definition we say what? The inverse of f exists. So if f exists, now we can get. So one way is, now you can change the position of x and y as you see like this. So this is one way of your solution. But it's advisable to write f inverse in terms of its domain. So you know here, if f inverse is written like this, it doesn't mean that domain of f is x is something like this. It's not the domain. So we need to rewrite like as its domain. So that means you start by putting f of x equals to y, which is 3x minus 2, then solve for x, so you get this one. Then the other after you solve for x, the next is put f inverse of x in place of x and substitute y by x. So that's how you get this one. So this is our inverse of a function f. So this is a formal way of writing the inverse function, and this is advisable to use always. So because it helps you to find the domain, range, and everything easily. So another is, so if you have given a function, then what does the direct image and inverse image of the given set under the function f? So if you have a subset subset of x, then we say a direct image of a under f is f of a, so which is a set and which is a subset of y, and which is given by f of a, means the set of all f of x's functional value whereby x is taken from a. So we say this is a direct image of A under F. And if you have B subset of Y, then the inverse image is again, which is a subset of X defined by this one. So remember that way. So do not, like we say, this F inverse, which is inverse of a function. But here F inverse of B means what? Which is a subset of X, which is a set. It's not a function. This is a set, but this is a function. So they are different. So this is X says that F of X is a member of B. So these are two important things you need to remember. So we'll use it later. So this is a remark. So because the inverse image is not the same as the inverse function, so as I explained before. So for example, now let F be from R to R, then be defined by F of X equals to X squared. Then, so this is, the example is just to justify or to elaborate this statement. So what is F inverse of this one? F inverse of 4 is set of all x's, says that F of X is equals to 4. That means F of X equals to a member of this one, means because the member contain only 4, that is this one. So which is x square equals to 4. So the elements of R giving their square is equals to 4 are this one. So this is a set. As you see, this is a set. So it's like B. But as you see, F doesn't have an inverse. Why? As explained before, X square like this one is not a one-to-one function. So if it's not a one-to-one function, then it doesn't have an inverse. So that means, remember always, the inverse image and F inverse of the inverse function are not the same. They are different. So let's see some important results. So if F from X to Y, a map, or a function from X into Y, and B is a subset of Y, then F composed F inverse of P is always contained in what? In P. F composed F inverse of P is contained in P. Now let's see the proof. So what does it mean? Now let C be an element of F inverse of P. Then what? So which implies that, so then we have what? C means C, which is equals to F of B. So F of something, remember that this is F of something. So let's say this is B. So which implies that this is like, for, you can say, for some F of B, which is B in F inverse of B, means what? F of B is in B. So we are done. Therefore, F inverse of B is contained in what? In B. So when this subset can be changed to equality. So let's see, that's a corollary down. So this subset can be changed to equality if and only when the function is an onto function. So the function is an onto function means, by definition, we said, for any element y in Y has a pre-image X. Says that F of X equals to Y, we said. So it's like, so if we take, let's B an element of B, we need to check the equality, because we did this part, we did this one, so we need to check this side. That means you take element from B, so which is subset of Y, and as you say that since the function is onto, then we say there exists X in X, say that f of X is equals to B. We say that one. So f of something, so let's assume that this is like f inverse of B, then we are done. So it's easy. So the next is, if f is given like this and you take subset of X, and we say this A is subset of this one here, so for each subset A in X, A also contained in what? In F inverse composed F. It's always falls true. So that means, now let's suppose, so we have given that A is subset of X, and let's take any element A from A. So what's this one? So by definition of inverse image, now we define this one like X, say that f of X is element of f of A. So which means that X says that f of X is, f of A means what? F of A, the set containing f of A says that A is in A. So since A is in A, now we have what? F of A is in f of capital A. So therefore, show that A is a member of f inverse of f of capital A. So we are done. So similarly, you can ask that when do you say that this inclusion is changed to be equality? So the corollary tells this one. So if f is 1 to 1, remember before the previous one we say f is onto, but here if f is 1 to 1 and A is subset of X, then there is an equality. So similarly, we checked for this part here, so we need to check for this one. So let X member of this one, take this one. Then by definition, so f of X is a member of f of A. So which means that f of X is equals to what? F of small a for some A in A, because it's a member of this set, means there is some A in A, says that f of X equals to this one. But we said that f is onto, I mean 1 to 1. F is 1 to 1, so that means what? This one is equals to this one, means X is equals to A, which is in what? In A. So we are done. So with if a function which is both 1 to 1 and 1 to, we call it the bijective map, or a 1 to 1 correspondence. We say there is a 1 to 1 correspondence between, like if f is a mapping X into Y, then we say f is bijective if it is 1 to 1 and both onto. Or another way is we can say that there is a 1 to 1 correspondence between X and Y. So this is an important thing also. So for example, now f of X is given by to the power of X, which is an exponential function. So the graph look like this, which is to the power of X. As you see, if you use geometry, yeah, it's if you use the vertical line, the horizontal line test, you see the graph, the line crosses the graph exactly 1 point, and if you draw the horizontal, I mean the vertical one also, the graph crosses the line crosses the graph exactly at 1 point. That means this function is a bijective function. So this is geometric proof. but we can prove algebraically also. So now I always said that you need to always start by checking the well-definedness. So this is, you start by x equals to y, two equal elements from the domain. Then if you apply the power here, then you'll get this one. So which means f of x is equals to f of y. That is well-definedness. So if the function is well-defined, then the next is what? Needs to check one-to-oneness. So you start by taking two equal elements from the range here, f of x is equals to f of y, from this one I mean, then which means 2x equals to 2y, then applying the logarithm function to base 2, then you see this will be cancelled using the logarithm property, and you get this is the same as x logarithm of 2 to base 2 equals to y logarithm of y to base 2. So this is equals to 1, this equals to 1, then it remains to x equals to 1. So we say the function f is 1 to 1. It's 1 to 1. Then the next is ontoness. So we have, remember that you see it's positive and excluding what? 0. So this is like a domain of logarithm function, the logarithm function. So let's take y, a member of 0 to infinity, then y is equals to what? To the power of x. So the question is, can you find that x? So yes, we can get, because you can apply both sides the logarithm function, because you see this y is in the domain of the logarithm function, so it's defined. So logarithm of y to base 2, which is logarithm of 2x to base 2, then which is x logarithm of 2 to base 2, and this is 1, so which is x. So for any elements from this set, we can find an element from here r, which is given by logarithm of y to x, says that x is equal this one, so we can get that x. Therefore we say what? F is onto. Therefore f is bijective. So this is all about today's class. So